So section 3.7 number 4 reads, if the radius r of a circle, the radius r increases at the rate, that's dr dt increases, that means what? Positive. At the rate of 9 centimeters per minute. Find the rate of change in the area. Find dA dt when r equals 8 centimeters. And they have it when r equals twice, when r equals the second part, 30 centimeters. First thing, I need to find an equation that will tie the area to the radius. We're talking about a circle. The problem state we have a circle. Is there an equation that will tie the area to the radius? What's the area of a circle? Pi r squared. Now let's take the derivative, and all of these the derivative with respect to time, because they're talking about centimeters per minute. So you're talking about per time. Find the rate of change for the area. They want it in, this will be an area, centimeters squared per minute. So let's take the derivative with respect to t. This will be dA dt. Pi is a constant, it sits in the front. What's the derivative r squared? 2r times what? dr dt. And plug in what you know now. What's the rate of change? There's the pi times 2 times r. What's r? 8. And what's dr dt? 9. Do the math. 9 times 8 times 2, 144. Pi. They probably want you to leave in terms of pi.
Yeah.
Yep. That's part A.
I'm sorry, where would that 9 come from?
dr dt.
Oh, okay. Sorry.
For part B, it's the same thing, except they're asking when r equals what? 30 centimeters. Everything is the same. So what's the change in dA dt? Pi times 2 times r, which is 30, times the 9. 18 times 9, is that 540? pi. On the test, like if we give you a sphere or something, I'll give you the equation for that. Like the next question Nick asked, number 5, talks about a sphere. The sphere increases at the rate of 9 inches per minute. The radius r of a sphere, so we have a sphere, it's like a basketball, that's 3-dimensional picture by me. I can't do it 3-dimension. That's a sphere. The radius is increasing, that's dr dt, at the rate of 9 inches per minute. Find the rate of change of the volume. When r equals, very similar to the other one, is 9. So we need an equation that will tie the volume to the radius of a sphere. Yep, the volume of a sphere is 4/3. You don't have to memorize that, but it's in pi r cubed, I think. If you have the book or the online book is on the chart. If not, just go to Google it. It says volume of a sphere. You end up with that equation. Take the derivative of this with respect to time. Now 4/3 pi is a constant, sits in the front. What's the derivative r to the third? 3r squared times what? dr dt. What happens to the 3's here? They cancel. So you end up with 4 pi r squared dr dt. Fill in the blank now. 4 pi. Do we know what r is? 9. Square it. Do we know what dr dt? 9. 9 cubed. That's 3 to the power of 6 times 4. 2916. I think. Uh, 9 squared times 9 times 4. 2916 times pi. Second part is change r to 30 or 35. It's the same thing.
Just out of curiosity, why do they use a uppercase R instead of a lowercase r in this?
That's me.
Oh, that's you.
R?
Oh.
I'll mix and match. There's nothing, you know. Depends what mood I'm in. I'm not consistent with that. Yeah. I just write uppercase, lowercase. Number, actually, the next one, they give you a cone there. And they give you the equation for that. I'll take a peek at it. Number 6. The formula for a volume of a cone. A cone, you can have it upside down or standing like this, or it could be standing like that, doesn't really matter. The volume of that, they give us the equation, 1/3 pi r squared times h. That's the equation for it. Control minus. Everything is big. I can't read anything. It says the formula for the cone is this one. Find the rate of change of the volume. What's dV dt? If what? If dr dt equals 9, I think it's inches. Let me just slide it to control minus more. It's 9 inches per minute. And h equals 12r for this example. They try to make it easy on us. H equals 12r. If you know what h is, plug it in. And make sure you only have one unknown. Otherwise, if you leave h in the equation, when you take the derivative, it's going to be the product rule. And it's not going to be that nice. Notice if I leave the h there without doing the substitution, it's going to get 10 times uglier. So what I'm going to do, I'm going to take this equation now. Since they tell me what h equal to, take h out and put 12r in it. Make life easy on me. If you only have one unknown, when you take the derivative, there is no product rule, there is no quotient rule. Well, it could be a quotient if it's a fraction. So play with the math. What do you have? 4 pi r cubed. They want to find dv dt when dr dt equals 9 in part A and also r equals 5. In part B, r equals 27. So we can plug it in later. So what's the derivative? dv dt. 3 times 4, which is what? 12 pi. Here we go. What's the derivative? That'll be r squared times dr dt. 12 pi. R is 5. Square it. And what's dr dt? 9.
Where did it say? R was 5?
Right in part A. It says part A, part B. Right above it says r equals to 5, right? So you plug it in. And if you do the math, 25, that's times 4. That's 400 times 9. Is that 2700 pi? Part B says r equals what, 27? 7 is ugly. Can't visualize the picture. But number 7 is we have a swimming pool. But usually the pool goes like this from the top, looking at it. The top, but the bottom usually is not a box there. The bottom is on a slant. If you have a pool, usually you walk in through it slowly. There's a deep end, shallow end. I think that's what this one looks like. Let me see. Or it might be like this, looking from the top. In one section, the bottom will be flat like this, then it goes up. I'm not sure what this one, if this is one of these. But that's normally what a pool looks like. They have the deep end and the shallow end. In the shallow, there's gradual one, or gradual, then flat again. Let's see what that picture there. A swimming pool is 12 meter long by 6 meter wide. One meter deep at the shallow end. So it doesn't go here, it goes like this. I'm not sure which one of these pictures we have. I'll put both. 1 meter. If I finish reading it, maybe I'll figure that out. And 3 meters deep at the long end. Water is being poured into the pool at the rate of 1/9 cubic meter per minute. I think that's the kind of pool they're talking about. Because it doesn't say we're flat for this far and it goes up. There's a picture there, but I can't visualize that picture. So the volume is changing at the rate of 1/9, adding, that means increasing, cubic meters per minute. And there is 1 meter of water at the deep end. At the deep end, so far we have 1 meter of water. So on this end, so water so far is this high. That's the water there. It's 1 meter high at the deep end now. What is the percent of the pool? What percent of the pool is filled? I think the first question they're trying to see if we understand what we have here. So we don't have that picture. Let me get rid of that picture. I was about just to cut the whole page out, but I have the white out. I can just. So I thought maybe it will look like this. You gotta look at the picture as two parts. So So the first question, what percent of the pool is filled? Well, let's look at the percent where the water is. What is the shape where the water is? It looks like this. Isn't it triangle? That's 3 feet deep. So that's the 2 feet. The 2 feet, because once you hit 1 foot here, 2 feet to this, then after that, it looks like this, the pool. Looking at it from the side. If you just take that dirt out and look at it from the side, not from the top, you see this is 2 feet, not 3, 2 to 1, because the whole thing is 3 feet deep. Meters, yep. 2 feet would be break your neck. 2 meters deep on this end. It goes on angle, then 1 meter up there. So for this, let's look at the bottom half. We'll call it the area for the bottom. BOT for bottom, TOP for the top. When you look at the bottom of this, what shape do we have? Triangle. The volume of any shape is the area times the height, or the width in this case. Now here is 12 feet, and the width from the top is 6, right? So you're looking at it from the front here, let's say it's glass pool there, and you see it looking like this. 12 feet long, has this shape, but how wide is it in that direction? 6 feet, right? So the volume for the bottom, we call it bottom, the area times the height. The area is 1/2 the base, which is what? 2 meters. And the height is the length of that, which is 12. It's a triangle. 1/2 this side times that. And what's the length of that piece across? It's times 6 feet. Is that 36? 72 cubic meters. And the volume of the top is going to be what? The top half is the rectangular shape. It's length times width times height. What's the length? 12. What's the width? 6. What's the height? 1. So what do we have? 60. Is that also 72? So what's the total volume? Is 144 cubic meters. Let's find out how much actually water in it. If we look at the water in it, the water shape looks like a triangle. Let's look at that picture. Bottom half. Let me enlarge that picture. This is what the pool looks like. The water only to 1 meter high. That's 1 meter. So I can't tell you what the volume of the water yet. Volume of water. We know it's 1/2 the base. The base is what? This is the 2 is all the way to the top. So this is 1 meter, right? 1/2 the base. Well, what's the length of that side? I don't know what that length. I have no idea what the distance from here to there. And how deep is it? Is it 6 feet deep? We got a problem. We don't know what L is.
It's not half the length.
No, because we don't know what the side is. Let me draw the two pictures side by side. Oh, maybe you might see it. That's the pool. And right next to it, that's the water. How do we figure out that side? Yes. Similar triangles, proportions. Yep. The ratio of this side to this has to equal the ratio of this side to this. 2L equals 12. What is L equal to? 6. Similar triangles. So if you go back to this now and plug in 6 for the length of that water there, it's 1/2, 1, 6, and 6. Is that 18? Meters cubed, not centimeters. So what percent of the pool is filled? 18 over, what was it, 144? And if you convert that to percent, you multiply by 100. What's 18 divided by 144? And you're going to multiply it by 100%, and that'll make it 12.5%. At that time, they want to know how quick the water is rising. We know the rate you pour in the water. We know the volume. We forgot about that part. That was given to us. So if you look at that ratio here, going back, redo the whole problem almost. Looking at that time, at that time when they're talking about, we're still in a triangle shape. This is 12, this is 2, and the water is being poured in. Let's call this the base of the water, and that's the length. We need a ratio between them. So the volume of the water at any given time, the volume, it's 1/2, that's B for the base. I'll use B here so you know. 1/2 the base times the L times 6. Two unknowns in that, not good. We just said similar triangle, the ratio of 12 to 2 is the same as L to B. Bless you. 2L equals what? 12B. L equals what? 6B. The ratio of this side to this is always 6 to 1. In this case. So if you replace L with 6B, L, which is 6B, times 6, 3 times 6 is what, 18? Now take the derivative.
Where'd you get 3 times 6?
1/2 times 6.
Oh, right.
3 times the 6. The derivative of that, 2 times 18, 36B times what? dB dt. The question is how fast the base is, the water level is rising. I call that the base. We're looking for that. If the volume, they gave us the volume early in the problem, 1/9. So this is 1/9. This is 36. The base is 1 when we talked about that. What is dB dt? You divide by 36. 1 ninth divided by the 36. You can multiply 9 times 36. Is it 1 over 324? Meters per minute. So guess what? It's going to take you a long time to fill that pool with water at that rate. But keep in mind, you're only pouring 1/9 cubic meter per minute. It's not a lot of, well, actually not a bad amount of water. But if you have a pool, you probably notice you have to leave the hose in it almost overnight completely for a couple of days to fill it. What's that noise?
Sorry.
Oh. So 1 over 324. That's how slow the base is rising. Then it's going to get worse, by the way. This is just to go this part. When you go to the top, it's bigger, the top. It's not a triangle, it's a full rectangle. That'll be slower rate even. So it might be 2-3 days before that pool is full. Good problem. I like that problem. I like all these problems. I think Number 8, very similar to this. They're showing you a picture of a pool. It's a V shape, so it's a triangle. You do the same thing. Number 9 is different. A construction worker. We have anyone who works construction here? Here's the picture, looks like this. And the person standing right here, and they try to move a piece of wood to the top. So the piece of wood is laying like this right now. It's 5 meters long. And we have a rope attached to it. So they tied a rope to this one, and they're pulling up on it, moving it up. That's the direction it's moving. They try to raise that piece of wood up there. So a construction worker pulls a 5-meter blank up the slide of a building. That's a building, I guess, the side of a building, not a slide. Tied it to a rope. And you can see the picture that says, assume that the opposite end of the plank follows a path perpendicular to the wall. So this one is moving, this angle is 90 degrees. So when this one moves up, this piece keeps sliding, sliding, sliding. It's moving in this direction. It doesn't just go up in the air. So assume this piece moves in this direction. As you're raising it higher and higher, it keeps moving along this line, making a 90-degree angle. And the worker pulls the rope at the rate of 0.16 meters per second. He's pulling up. So let's call this rate here, that's a velocity basically, d, let's call this height here, dh dt, or the velocity, is equal to 0.16 meters per second. That's the speed he's moving. Changing distance over time is speed. How fast is the end of the plank? This end is moving along the ground. If it is 2.5 meters from the wall, how fast this one? Let's call this distance x. What is dx dt equal to when x equals 2.5? Round the answer to 2 decimal places. Okay. The answer to this is going to be negative, by the way. Why negative? Shrinking, right? That distance shrinking. So if we call this distance x, we call this distance y. Can we find relationship between x and y?
Yes.
What rule?
Pythagorean.
Yep, Pythagorean theorem. X squared plus y squared equals what? 5 squared, which is 25. Take the derivative of that. Derivative x is what? X squared is what? 2x dx dt. The derivative y squared is what? 2y dy dt equals 0. We're looking for dx dt. 2 times, do we know what x is? Yep, 2.5 times dx dt. That's what we're looking for. Uh-oh, I don't know what y is. Do I know what dy dt is?
No.
Look at it again. You're moving this up at the rate of 0.16, right?
Oh, yeah.
That's dy dt actually.
H is y.
Yep, well, whatever speed this one's moving, that's also moving the same speed. Because they're tied with the rope, you're yanking on it. If the rope moves up at that speed, this piece is moving up at that speed. Now, here's one little problem. We don't know what y is. When x is 2.5, we need to know what y is. Go back right here. Put 2.5 for x. Y squared equals 25 minus 2.5 squared. What was it? Can't be. The whole thing is 5 feet. Right? This is the longest side. That's 5 feet. So what is y going to be? The square root of that number. 4.33. So now plug it in. How many unknowns do we see there? 1. When you move that number, that becomes negative 5 dx dt equals minus 1.386. What's dx dt equal to? Divided by 5, which is negative 0.277. It says use how many digits? 2 decimal places. Negative 0.28 meters per second. Negative means shrink in that gap.
That's positive 5 dx dt.
This one plus, yes. 2 times 2.5 is 5. This number is positive. When you take it to that side, it becomes a negative. And I think the last one we did in the class here, playing with the radar, going over a spot, Pythagorean theorem again.